Hey there, AP Pre-Calc people. Today we'll be finishing up lesson 5. We're going to start by talking about the natural base E. I'm sure you all have seen on your calculators, there's this magic button that says E, and it's not my report card. It's actually a magic number. Okay? It equals about 2.7182818282228. And it's a graph of, we call it the natural exponential function. Okay? It looks like y equals b to the x. But it's important to note that E is not a letter. It is a number. Just like pi, right? It is a constant, and x is a variable. Okay? E is a number. It's 2.718281828. Okay? How did they come about that? I'm going to be kind of brief and talk about it, not spend too much time. But E is the limit of 1 plus 1 over n to the n as n goes to infinity. It's kind of counterintuitive because 1 over infinity is 0, and anything to the infinity power is infinity. So if 1 plus 0 to the infinity power should be 1 or 0, who knows, or infinity. But it actually ended up being this weird number. I'm not going to get too much into it. It is intriguing, though, why it exists. I have a book on it if you guys want to read it. Or if you're too cool for that. For completionism, for those people who like to fill out their boxes, actually, for completionists, you guys can pause it right here and copy this down. It doesn't really matter. Just know that E equals that. Okay? Okay. All right. So, more review. We have our functions. We're going to use E for the rate of change now. Or not the rate of change, but for 1 plus R. Because we're just changing it to 1 plus 1 over x to the x, because it's going to be a growth or decay. It's a continuous. This model is continuous growth or decay. Okay? Where before, we were doing like a monthly or doubling time. This is continuous change. All right? If our k now up above is greater than 0, it means that E is going to stay positive. Or like not positive, but not a fraction. If k is less than 0, so negative, it's telling us it's a reciprocal of E, which will make it a fraction, which makes it a decay. Okay, so if k is less than 0, it makes it decay. If it's greater than 0, it's a growth. All right, so let's take a look. The atmospheric pressure P of commercial airline decreases as the plane height increases. All right, oopsie. It's measured in millimeters of mercury. It's related to height above sea level. The relationship is modeled here. Okay. So pressure is based on height. That's a negative, so that's going to be a decay, right? It's an inverse. It's going to be a decay. So what's its pressure at 4.5? So I'm going to plug in 4.5 for my H. And be really careful. You guys try to plug this in a calculator too. When I plug that in, I get 395.764 mmHg, millimeters of mercury. Okay. What's this pressure when I reach 10 kilometers? So I'm going to do P of 10. Again, be careful when you plug this in. So this should go down now, right? Because it's decay. Okay, 178.273 mmHg. All right, that's not too bad. Not yet, at least. Now we're going to change our half-life formula. Because it turns out half-life is more continuous than it is like an actual half-time. Now, it will kind of work. But we have a formula that we can use that I'm not going to get too much into. You learn it a little bit more in Calc. But carbon-14 we know is a half-life of 5,715 years old. It's accurate up to 80,000 years. It's not really that accurate past 80,000 years. So here's our formula. The half-life of a different substance, so we're not looking at carbon-14, is 24 years. A sample is 5.8 grams present initially. Let's write a model. Okay? So I have my A of T amount. It's equal to my initial, this is my A sub O, 5.8, times my E. Now what's my K? K is going to be equal to natural log of 2 over my half-life, which is 24. So I plug it in my calculator. If you don't know where natural log is, it's right here. And I got 0.0288811. Keep 6 decimals, guys. It matters, okay? Now my formula is decay, so it's going to get less, so I'm going to plug in negative 0.0288811 T. Again, I got that from using this formula. When will there be less than 1 gram remaining? All right. Man, we got to learn this. So when will this equal 1? All right, I'm going to grab my calculator. Do my y equals and clear. I'm going to plug in a 1. And I'm going to plug in 5.8 e to the negative 0.0288811 x. My window, it's messed up. I'm going to do zoom standard. Let's see if I get an overlap. Nope. Well, the half-life's 24 years, so I'm going to have to zoom out quite a bit. I'm going to change my window. X max, let's make 24-year half-life. Let's go through 5 half-lives and see what happens. Looks like I'm going to get it. Secondary calculate, intersect, enter, 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 enter. 60. So 60.867 years. Seems legit. Seems pretty good. Oopsie. All right. Let's do one more. Compound interest for yearly interest. You guys can read this. Give it a second, read it. So for compound, like if it's monthly, for number 1, my n's can be 12. So I'm going to do 1 plus r over 12 to the 12 times t. For continuous, I use PERT, my principal, my initial, times my e to the rt. Okay? We're going to use these formulas quite a bit for a little bit. So let's do this. A writer deposits $5,000 account that pays 6.25% annual interest. Bologna sandwiches. Compound continuously. Also bologna sandwiches. No bank's going to do that. How much will be in the account when you enter college 4 years later? All right. So I'm plugging in 4 years later. I'm using the PERT because it's continuous. I'm plugging in my initial 5,000 times E. My rate is 0.0625. To the T, which is 4. So I'm plugging in. I plug that in my calculator, and after 4 years, I have $6,420. No bank will give you that. That's too much interest. So you'll have about $6,420 when you're in college. All right. Hope y'all enjoyed. Have a good day.